Hi, everybody. Seem like we're in okay spirits, despite Project 2 looming and being done. So I'm going to kick off today by talking about some life lesson stuff, which I like to do sometimes. I'd like you to think about this problem that's been up on the board, which is, to what degree do you believe the following? Nearly anybody enrolled at Berkeley, you're in the door somehow, could achieve an A in 61B. And let's assume you could spend the entire summer preparing beforehand, you can hire a tutor, whatever's legal, reasonable, and can happen in one person's lifetime. So just think about this, submit an answer if you get a chance using the link up top, or not. So just think carefully about it for a second. I'm curious what your opinion is. Maybe this time I'll bring it up. Okay, this time I'm going to freeze it before I show you the answer. Okay, I'll wait another 10 seconds. Okay. So I'm just getting a landscape of your sentiment as a course about how you feel about this question. All right. So at the moment, at least the people who come to lecture, there's going to be selection bias. This is the rough balance, right? So in terms of who thinks you could definitely do it, 18% roughly strongly agree it's possible, 27% agree, 40% neutral. So basically we have almost half optimists, people who aren't quite sure, and then 40% pessimists, a little more, right? So it's actually pretty evenly spread, interestingly. Okay, so that's just the lay of the land. So I'll tell you what I know, or what I have a sense of this question. I think it's a really interesting one, right? So as someone who works as an educator, I mean, ideally everybody just gets an A. Like, that would be a good result for me as a teacher. Doesn't seem to happen. So I'll just bring up, at this point, in the year 2018, a large number of you guys have heard of this model that Carol Dweck has. And so in her mind, or in her model, students, you can divide them into having a growth mindset or a fixed mindset. And very, very, very crudely speaking, you could map the folks who are pessimistic to the fixed mindset and the optimists to the growth mindset. Now, it's not a one-to-one mapping. It's not perfect. But roughly speaking, in a fixed mindset, students believe that their basic abilities, intelligence, talent, etc. are just fixed traits. You have a certain amount, and that's that. And then when it comes to things like office hours or lab or discussion, your goal is to look smart and never look dumb. And in this approach, having to put in effort is a sign of weakness. I mean, certainly I remember that, and you guys remember this from high school, where there was a brag you could make where you said, well, I didn't even study. And that would make you cooler or better, right? Because your brain's so good, you don't have to do the work to get somewhere. Now, in a growth mindset, by contrast, and again, this is Carol Dweck's model, she says, students understand that talents and abilities can be developed through effort, good teaching, and persistence. They don't think that necessarily everyone's the same on some deep fundamental level. Presumably there are some people that work faster than others, and that's just something you gotta live with. Or that anyone can be Einstein, but they believe that everyone can get smarter if they work at it, where smarter means something, all right? Now, growing up, and definitely all the way through undergrad, I was very, very fixed mindset, like 100%. And it has to do a lot with just like my upbringing. Like when I was a kid in school, I hated coloring, and my first grade teacher let me do a math grade worksheet from her third grade class instead, so I didn't have to color. So I got a head start. I started programming when I was 5 or 6 or something, because we had a computer that my dad bought, and it was like a basic computer where you couldn't do anything hardly except play video games, or there was a book where you could type in programs. And I didn't know what I was doing as a programmer. It was nothing rational. I was just typing stuff out of a book when I was 6. But I had a lot of advantages, and early on I just was ahead of people, and people said, hey, you're good at this. And that was just my sense. Like, I'm good at it, some people are not, and that's good for me. That was my sense. Now, it was much later in life, whenever I got to late in undergrad, where I was like, oh wow, everybody's really smart, this is hard, I have to work a lot. But just to give you my sense of where I started, I was very fixed mindset. But over time, I've definitely come around much closer to a growth mindset, personally. One of the pieces of educational psychology literature I find particularly compelling, actually it's pretty old, from the early 80s, there was a paper by Benjamin Bloom where he did an experiment where he took students and randomly decided, you were in a regular class, like this huge one, where you guys just show up, in this case it was 30, so for you guys it's a little bigger, but slightly. But you all get dumped into an arena together, and there's all these different resources, but the class moves at a fixed rate. It's like clockwork. Like Project 2 is due Monday. Okay, that's just how it goes, and everyone's on board. That's the conventional class that he studied. He also did another thing called mastery learning, which I won't talk about today, but basically it just means students work at their own pace and they work until they complete objectives and then move on. And then there was one-on-one teaching, which is, imagine a world where you just hire me personally. And I just come to your dorm and I just teach you computer science. That's it. There's no lectures. There's no any of the stuff with labs. I just sit down with you and we start talking. And then I ask you some questions, and you program, and I'm there to say, no, don't do that. You need to use tab completion, or no, try using the debugger in this way. And there's never a moment where you're flailing and spending 3 hours trying to debug something and moving pieces of code randomly and hoping it works, right? That's tutorial learning. Now, they all took the same exam, or some very similar assessment, and this is like in I've actually forgotten now, but it's like middle school math, or maybe early high school math. It was 3 different classes they did this experiment. I've actually forgotten the details now. It's been a couple years since I've looked at the originals. But when you looked at people's grades, this is basically a histogram of how they did. And it's obviously just a figure capturing the essence. This is not the raw data. Where this is basically saying there were a lot of students in the conventional lecture who got let's call this a 60%, because that's 60% of the way to the right. So the average grade among the conventional, everybody thrown into the arena together, was 60%. The students who were one-on-one tutored, their average was much higher. In particular, it was around the top 2% of the conventional lecture. So you take somebody who was in this class, and instead you do the Josh Hugg coming to your dorm room class, maybe, and they would maybe end up in the top 2%. Okay? So I think it's a really interesting result. Now, there have been subsequent papers that assess, and the reason it's called 2 sigma is that's around 2 standard deviations above the mean. So this notion of being 2 standard deviations above the mean, I'm guessing for a lot of you at Berkeley, it feels like something you have to be born with. That some people, it's like Harry Potter, like, okay, you just happen to have them extra, midichlorians or whatever, and that's the only possible way you could get up to that top 2%. But this experiment seems to show, at least in this specific setting, to be the opposite. Okay, so I think this is really interesting because there's a lot of assumptions that you guys make as students that you don't think about that might profoundly affect the way that you go about your lives. So this is an experiment in the general sense. So I did a similar experiment, kind of, in spring 2016. So at that point, there was a rule where if you failed a class, you could retake it and then get a new grade, and that would maybe get you into the major. And I'm very sensitive to the fact that a lot of you guys are fighting really hard to declare CS. Like it feels, and again, not making it doesn't consign you to a life of misery or anything, but still, I know it's important. And there's a lot of people who really want to go to the major because it means you can actually get into the classes more easily, and it also gives you a nice credential to go brag about. So I, being sensitive to that, said, okay, spring 16 class, if you want, at the end of the semester, you can give me a condition. If I get less than B, fail me. Right? And that allows you to retake the class in theory. Now, I got in trouble for doing this with a dean. They were very upset. They thought I was making a game out of the grading system. But the problem was the rules had been set up so that the rational thing to do was to game. And I knew that students would fail intentionally, and I said, rather than you waste your time and intentionally fail, why don't you just take the final, come in, maybe you do well enough, maybe you don't. And so I had around 30-some people take me up on this offer and actually failed the class intentionally. I took the heat, and this loophole's been closed now, so it doesn't matter. But it's actually very interesting because I have a grad student, we're like studying all these things about how people do as they move through the program, and what I found is that students who took the class the second time, they did on average 2.5 letter grades better the second time. So somebody who took the final and they ended up at the, somewhere around the low end of B, or sorry, the middle of B. They got the grade of B, but in the middle of that range. On average, they would be about the bottom end of A. Okay? Now that's actually really different because, I'm not going to talk about all the data in all the world, but when you look at students who go from 61A to B, they tend to not jump like that. They certainly don't, on average, get 3 letter grades higher and 61B than A. However, students who took 61B twice did a lot better. And this is just an experimental result. And there are people who were like 5, 6, 7 letter grades higher the second time. So a possible interpretation is that there's something we could be doing as instructors to tell you how to prepare better so that you could actually achieve your dreams. I have not found it yet, but it's a goal as a teacher professor, something I'd like to find. So the point here is just to say that if you've struggled in this class and you feel like maybe I don't have the quintessential thing that's part of the soul of a programmer, I think you're probably wrong. Okay, that's my guess. All right. Any thoughts about this before I move on? Yes. Yeah. 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 Yeah, so time spent obviously has a huge impact on how you do in a class. And even in my fixed mindset early in college, felt like I was killing it days. I remember sitting in the study room at the end of this hallway doing calculus problems for 8 hours one day, because I really wanted to get an A in that class. So that's a big deal. Now, one thing that's really important is efficiency in how you spend your time. And, just sitting down with you guys in office hours, I can smell the inefficiency and the way people are approaching things, because sometimes it's easier just to try and do more of the same thing that's slow than to try and do something faster. Like debugger use is a classic one, and that's a tricky one. And I think there are people who just work more quickly because they have more background. And yes, I actually personally think there is some innate brain thing that at least, I don't know if it's at birth, but maybe by the time you're 5, something about the way you play, I don't know what it was. But I do feel like there's some people who just move a little more quickly with this type of thing. But I think it's surmountable. And I don't think it consigns you to not be really good eventually. It just takes longer to get good. Other thoughts or questions? Yeah. 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 Maybe it's not a great framing, but yeah. Oh, should you be expected to prep? No. I mean, there are people who come in without doing any extra special prep. But for the people that are super hungry to really do this, they email me before. They're like, can I do all the homeworks? I'm like, sure. So, yeah. I don't expect it. But that's life. I mean, there's if you want to get real good at stuff, sometimes you just pour your soul into it. I'm glad that in the United States we don't have to spend 2 years of our life studying for entrance exams like some countries. So, but sometimes it's handy, Any other thoughts before we move on? Yeah. I'll take 2 more. How would I answer? I think I'm probably in the strongly agree camp, maybe agree plus. Yeah. Just having done that other experiment. Yeah.
Judging by what you said about students taking CS61
Yeah.
not just make a course to help students prepare for 61
Yeah, so that was what should be the right prep? I know there exists some prep. So in theory, 10 is the preparation for A, and we've been studying whether or not it super helps. But it's a good point. There used to be self-paced 61A. Maybe we could do something similar. Who knows? All right, I'm going to move on. But I just wanted to bring this up because I think this stuff's really, really important to be thinking about. And yes, I used a whole lot of our class time about binary search trees today, but we got to do it sometime. Now I'm going to talk just a little more about life in a minute, but first some announcements. Homework 2 will be due next Wednesday. It'll be out late tonight. You can actually do Spring 17 version if you're really, really itching to do it before it comes out, and it'll be almost the same. This is not true. I know the midterm 2 date. I don't know why that's there. Actually, it's there from last time, but I fixed everything. If you're somebody who wants to talk about your Project 2 experiment, there's a link here. I'm not going to say anything else about it, but if you wanted to sit down in a room with me and talk about it, that's a link. You can do that. All right, Project 2, reflecting on it. Some lessons. Designing the API of something is extremely hard, and the first design you come up with is probably going to be super ugly, and probably the last one you come up with, and the constraints you have in this class, also probably still ugly. Second, modular design is important. If you have a modular design, it's easy to do play with keyboard and play with input string separate and have them share code. But if things aren't modular, then maybe you had to do some hacks. And it's okay if that's where you ended up. But now you know. You've seen where things can get bad. Hopefully you've seen now that if something is ugly and it actually works, then you can actually refactor your code so that it still works but is less ugly. So refactoring is where you take that giant blob of mess and you just make a new thing that does the exact same thing but is now cleaner. So hopefully at least some of you got a chance to refactor some code. Hopefully you also saw that your choice of classes, like how things are organized, whether or not you have a room class or whatever else, or what data structures you use, can make a big difference in how hard your code is to implement. And then lastly, that working on a team, well, that's hard. Talking to people can be a pain in the ass, but it can also be wonderful, and you get to see how it goes. Now, if you want 61B, we're done with this. We're not going to do massive design projects anymore because we just don't have, we have a lot of things we actually want to cover that are specific knowledge. So from now on, it's going to be a little more on the rails. But if you want to do this kind of thing more, 169 is your class, or if you go do an internship, it's going to feel maybe a little like this, though not so much from nothing. So homeworks in Project 3, not going to be like this. Sorry. All right. Midterm 2, how do you do better? Well, I'd say going through the study guides. The study guides for the second half of the class are much more mature than the first half. They've been around a long time. I would work on the problems independently and then discuss solutions with others. Arguing is important. And that's that, I think. All right. So those are my other life thoughts. All right. Any other questions about this before we finally get to talking about binary search trees? Yes? There are no solutions to the guide problems for the most part because I want you guys to argue about them. because the solution is much less useful to you than the argument that gets you there. Personal philosophy. You're welcome to develop solutions and share them amongst yourselves, but as a point of order, I just don't want to provide them. All right. Okay, let's talk about binary search trees. So let's start by talking about maps. So maps have a number of operations. Get, size, contains key, put, clear. Clear just deletes everything in the map. So let's talk about an ordered linked list-based map that goes from character to we don't really care what. And this is what it might look like. So suppose our keys are the letters A, B, C, D, E, F, and G. And so put, for example, we could associate the letter F with fox, and D with dolphin, and C with potato, whatever. All right. So this is a way we could build a map. And actually, in an earlier lecture, we did an array-based map. Okay, so here we'll notice that I'm only showing the keys. I'm not showing that D goes with dolphin or F goes with fox because I don't care about those. I'm just showing the keys. And in an earlier lecture, we actually built the map, totally, the whole thing, based on unordered arrays. And here's a link back to that. But in this approach, what we're going to do is use an ordered linked list. So given these operations, take a minute to think, out of these 5 operations, which ones will take worst-case linear time, or at least identify one? So think about that for 30 seconds or so. All right, there's a bunch. Get contains key and put, all worst case linear time. If you want to know if the list contains F or the map contains F, you got to iterate. There's no way around it. Clear, you can just set sent to null, maybe, or to some dummy node, I don't know what. And size, you can just access quickly. Okay. So we want to do better. Yes? Put is not login because if we want to associate G with, I don't know, horse, then we have to step through to find G. Make sense? Yeah, so putting, we still have to associate the key with a value. Yeah. Say again? Oh, well, with put, like say you would do put E, you don't know if E's in the list, so you have to actually look in the whole thing. Yeah. So let's try and do better. Okay. So the fundamental problem is that it takes a long time to find what you're looking for, even though it's in order. We could, you can't binary search this because it's not an array. You have to follow the links. So one approach that would make things better, here's some little magic. Okay, I'm going to razzle-dazzle you guys. One approach is to add express lanes. Okay, so we can randomly say that, I don't know, A points at D and B points at G, and each node will have not just its next, but also some other random forward links. And this is something known as a skip list. We're not going to discuss it in 61B, but it's a cool data structure. And you can show that it has a randomized performance that is quite fast if you have random links. Okay? And it's dependably fast. So that's fun, but it's a little messy. Right? That's the pigpen approach. So I'm going to show you the more careful, straightforward approach, which is also pretty fun. Now this is that's like the crazy approach. Here's the real razzle-dazzle approach, which is let's take our front pointer and move it to the middle. Okay, that seems pretty good. But we have still an issue here, right? So if we move the sentence, or like the starter to D, what's the issue here? We can't get to A, B, or C. So what can we do to fix this? Okay, we can flip the links. So by doing this, we've halved the search time. If we want to get to A, B, C, E, F, or G, well, okay, great. It only takes half the time. Now, this is still linear time, but we could do better. So how do we do even better? Think about that for 20 seconds. Dream really big. How do you change the structure of this to make it even faster? And just think about this specific list. Don't worry about bigger ones. Okay. All right. What do you think? Give me an idea that doesn't involve express lanes. Yeah. Have D point to F and B. That seems pretty good. And then flip those. All right. So in this case, we've now built this kind of tree-like structure where we can hop our way down the tree more quickly. So we end up with this shape at the bottom. Those two are the same. What we've got on the bottom, we'll learn, is called a binary search tree. So we've razzle-dazzled ourselves from ordinary, just an ordered linked list to a tree. Good. Okay, well, let me tell you, the thing we just built is called a binary search tree, and let's start doing some defining. So we've invented it. So let's be more careful about what this thing is that we built. Any questions about it, actually, real quick? Yeah. Does it mess up the order of the linked list? No. I mean, it messes it up in a way. I mean, it's no longer an ordered linked list. You guys will agree with me. It's now a tree. It's not a list at all. It's a tree. And so we'll see that this is actually a useful thing. All right. So let's define what a binary search tree is, formally. So what's a tree, first of all? Well, a tree, which we'll be seeing in a lot of lectures in the future, you've seen them in 61A if you took it. A tree consists of a set of nodes, a set of edges that connect those nodes, and there's one global constraint, which is there's only one path between any two positions. So, for example, there's a bunch of figures that are going to appear at the bottom, and the green ones are trees, and the pink ones are not. So that is a tree. It's a set of nodes, it has a set of edges that connect those nodes, none, and there's only one path, no paths at all. Okay, that's a more interesting tree. Got nodes, edges, one path. And then there's another tree. Okay, this one has 3 links in one of the nodes and 2 in another. But if you want to get from any node to any other, there's only one path. Here's a thing that's not a tree, because while it has nodes and edges, there's 2 ways to get somewhere. Like if I want to get from here to here, we can go around the long way or the short way. And another non-tree. All right. Cool. Now, there's also something called a rooted tree. In a rooted tree, one node is called the root, and every node except the root has exactly one parent. And that's going to be defined, the parent is going to be defined as the first node on the path from in to the root, where in is the node in question. Now, unlike trees, most of them, the root is going to be at the top of the tree, and we say that a node with no child is called a leaf. And in a rooted binary tree, we'll say that, so binary specifically is going to be a tree where every node has 0, 1, or 2 children, which, by the way, are themselves subtrees. So these 2 green objects here, those are both rooted binary trees. They're both rooted binary trees. And for both of them, A is the root, B is a child of A, and C is a child of B. Okay, and the parent is the opposite relationship as child. This example here, that is a rooted tree, but it's not a binary tree. All right, any questions about this definition? Okay, good. So we got trees. There's not a lot to them. Okay, so it's a nice recursive data structure that you may have seen in 61A. So a binary search tree, okay, is a rooted binary tree that has one additional property. It's not just one of these trees, like by structure, but it also has an interrelationship about the values in each of the nodes. So for the binary search tree property, we say for every node in the tree, every key in the left subtree is less than x's key. So we have for a node x in the tree, every key in the left subtree is less than x's key, and every key in the right subtree is greater than x's key. And because it's a recursive data structure, this needs to be true all the way down. So if we look at our binary search tree on the left, we have dog, and all of those items on the left, Alf, bag, and cat, are all less than. And that's actually true of all of its subtrees. So bag has the left, which is Alf, all smaller. Now on the right, we have an issue. This is a rooted binary tree, but it's not a binary search tree because of ears and fish. Specifically, what's the problem? So here's ears. What's bad about fish? Yeah. It's bigger than ears. That's no good. Okay? So that's a binary search tree. So we'll see soon that these are really, really useful. But that's their definition. So any questions about the definition before we move on? Yeah.
Why is the whole tree not a binary search tree?
Let's see. This right here, that's a binary search tree. But the whole tree, I'd say, is not. So the tree rooted in debt is not a binary search tree. But yes, this is a binary search tree. Yeah. So couldn't building such a tree take a long time? Well, we'll talk about building soon. Yeah. Turns out to be not so bad. All right. So there's an important rule about the binary search tree. So less than, with a string, we know what it means. But the ordering could be something arbitrary. It could be something else. So there's a rule for a binary search tree to make sense. The ordering needs to follow the rules you expect of an inequality. So it should be complete, transitive, and anti-symmetric. So in other words, given two keys, P and Q, either P is less than Q or Q is less than P, and it needs to be transitive. So if P is less than Q and Q is less than R, then P is less than R. Now, one of the consequences of these rules that I've just made up is we don't allow duplicate keys. We can't have two dogs or two flats, just not allowed. Okay? And the reason we do that is it keeps things simple in terms of our reasoning about how all the different operations should work. Now, you might say, but sometimes I want to store multiple things in a data structure. Maybe we would have multiple dogs. Well, there's ways around it, but most real-world implementations, like the implementation of these binary search trees in Java, it has the no duplicates allowed, and any textbook is going to be no duplicates allowed. And we won't talk about, but the study guide will have an example of a question about what do I do if I want duplicates? And I'll spoil it with a boring answer that you just store in each node a list of how many there are, okay, or something like that, or you store a list of all equal keys. Okay, that's kind of not the important point. The punchline, if your eyes started glazing over once I started saying complete, transitive, and anti-symmetric, the important point, no duplicates allowed. That's what the slide's really about. Okay? So let's talk about how you'd actually do operations on a tree. Like, how do you know if something's in the tree? How do you build the tree? Where do they come from? Well, let's talk about search first. So let's just say from the heavens, somebody provides us with a binary search tree. Where did this come from? Who knows? Okay. Well, the process for finding something, right? Because remember, it's a map. So the map takes a key and it gives you a value. So maybe it tells you how many elves there are. So you look up elf and the value is 95. Well, that means then that we need to be able to find elf. Okay, so the recursive algorithm for search is if the search key, the thing we're looking for, equals the label of the node we're looking at, we return and say that's the node we want. If it's not equal, then we'll go, if the search key is less than the label, we'll go left. If it's greater than, we'll go right. So let's do it by example. Let's see. Can we do it by example? Let's try. I'll do it out loud. So let's say we want to find elf. Okay. Or actually, let's do cat. All right. So we look at cat. Is cat equal to dog? Surely no. Okay. Is cat less than dog? All right. So that means we recursively start the search over at bag. Okay. Is bag equal to cat? No. Okay. So then is cat less than bag? No. Okay. Is cat greater than bag? Yeah, so we go there. Is cat equal to cat? Yes. So then you return that node. So that's search. Okay, so that's what the search process looks like. It's very intuitive and actually very fast. I mean, as we'll see. All right. What would the code look like for this? Well, roughly, this is pseudocode. And in the binary search tree and hash map lab, which will be a week from this week, because we're doing demos this week, you'll get a chance to actually write this from scratch. But the pseudocode looks like this. Given a binary search tree, T, so it's a node, so you can think of this as BST node, and a search key, we find the BST that we care about, so the specific node we want. If it's null, we return null. If it's equal, if the key is equal to the label, so the label, let's imagine that label is a function that gets back, whatever the value is, in this case, dog. If they're equal, we return T. Otherwise, if it's less, we call this function recursively on the left. Otherwise, we call it recursively on the right. So the code, not so surprising. And I have this funny little less than symbol to capture the fact that, in Java we would have compare to, and it would be ugly. So pseudocode. All right. So how fast is it? Well, I'd like you to think about, and this is a very ill-defined question, but I still like it. Okay, it's, suppose I have a tree which is bushy. What do I mean by bushy? I mean that if you were to fall on it from below, from a great height, there's all these branches that catch you. It's nice. It's a big, comfy bed if you come at it from the underground direction, right? Look how bushy and wonderful this thing is. So if we use search on a tree of n nodes that's super bushy, how long do you think search will take? Just use your intuition because we haven't defined bushy. So n in this case is 15. And so if n is 15, you think, does it take around 15 looks? Does it take less? Okay. So it seems like a large number of you believe it to be log n, and indeed, that's true. So if you search this tree, it's going to finish really quickly in log time. So if I have n nodes, I don't need to look at all n nodes. I follow one path. And if I don't find it, do I need to search more? No, why not? It's not there. So if you get to the bottom and the thing you're looking for is not there, it does not belong to the tree. We've fallen off the tree. That'll be what this base case is all about. Okay? So in this case, the height of the tree is what matters. That's going to be the number of inspections. If our cost model is looking, which seems reasonable to me, then that'll be the overall runtime. It'll be log n. Okay? About. All right. So the takeaway here is that if you use a binary search tree as your map or your set, and it's bushy, then it's going to be incredibly fast. So if we have a tree that's 10 to the 300,000 items, which is a lot, I think, it'll take only around a second to find something, even if we're only doing 1 microsecond per operation. Okay? So I'm saying that an absolutely unimaginably giant tree, far larger, just unimaginably larger than even the most unimaginably large things, double unimaginable, still going to be very fast. Now, because of the fact that in the real world, much or even perhaps most computation is dedicated towards finding things in response to queries. Imagine you're on Facebook and you start looking for someone's name, okay? That's a search. I go to Google, I look for something. That's a search. I try and send an email to someone. Well, somewhere some database is going to look up something about me and then deliver the email appropriately. There's so much querying going on out there. And so it's a good thing that queries are basically free. That the world's information doesn't get anywhere near this level in terms of number of bits, and yet, and because of the fact that we have fast search structures, like this binary search tree, once they're built, then we can query them very quickly. That's an incredibly important thing, okay? Now, we'll learn actually in the 2 lectures from now that search trees are not used quite as often as something else known as a hash table, but search trees actually work pretty well. Okay? Now, how do you actually build this thing, okay? So perhaps I've convinced you that they're very fast for search, but you actually have to have the, you could build the list and then flip all the arrows, but that seems way too complicated. And what if you already have a tree? How would you add something new? Well, it turns out it's actually really easy. All you do is look for the thing someone's trying to insert, and if it's not there, put it there. Okay? So let's just try it by shooting from the hip a little. So let's say we want to insert the key eyes. Okay? So if I want to add eyes, which is the equivalent of trying to associate eyes with some value, because remember we're trying to imagine implementing a map. We go to dog and we say, is dog eyes? Nope. Okay. So is eyes smaller or bigger? It's bigger. So we go to the right. Is flat eyes? No. Which way do we go? Left. Okay, we get to elf. Is elf eyes? No. Okay, so what do we do? Well, we need to add a new node and link it below elf. Okay, so we've now built a new node, and that's what the insertion process is like. So we just look, oops, it's hard to do. Okay, yeah. So we just look for it. If it's not there, we set it equal. Okay? So you can imagine writing code that does that. It's not going to be too crazy far-fetched to do. Any questions about the insertion process? Yeah. Sure. Which one? Say. Could we define what bushy means? I would say that a bushy tree is one where the height is around log n. Okay, yeah. All right, here again. Yeah. Why would elf and eyes, why should they be reversed? Oh, we're actually looking at the whole word. And since eyes comes after elf in the alphabet, it'll go here. I mean, there are alternate insertion procedures, right? Like this is the simplest search procedure I can imagine. There is another one where eyes ends up here and elf ends up below. But I'm gonna say that my insertion process, you always put it at the bottom. It's always gonna dangle off the bottom. Okay? So that's just the way I'm gonna decide to do insert. Now, if you think about what that process is like, where we actually added in eyes, that meant we needed to set elf's right pointer to eyes. And so you will get a chance in lab to actually write this code, but I'll give you a little taste of what it might look like, okay? So insertion is a little strange, and it actually has the flavor of the destructive sans code from midterm 1. So that pattern you saw on that problem and that you saw in the labs and presumably you saw on 61A is actually very common. So it's a strange piece of code. I'll just give you the flavor of it because we don't have the time to really inspect this code in great detail. It's more fun to do on your own anyway. But when you insert, Basically, it works like this. If T is null, you return a new binary search tree node that contains the key that you're inserting, the insertion key. However, if it's not equal to null, we haven't fallen off the tree, then what we do is we say if the insertion key is less than the label, we're going to reset t.left equal to the result of insertion below. Now, this is a really important and subtle concept because it doesn't feel quite like what you want to do. It seems a little strange. So imagine that we're inserting eyes or something, or like zebra, okay? So when we start, we say, is zebra equal to dog? We got it. No? So in that case, what we do is we'd say t.right, this node, equals the result of insertion. So we're resetting this pointer, which seems a little strange because it's not going to change, as you and I know. Zebra is just going to end up over here. So there's going to be a lot of assignments here that are redundant. And yet, this is the cleanest and best way to write this code. Okay? Now, again, that is something that is more deeply understood and just richer and more beautiful when you have done it yourself. So that's what that lab's going to be about. But be aware, this is the cleanest version of the code. And if you sit down, like, say tonight, wake up in the middle of the night, cold sweat, want to write the insertion operation, get up. Great. Have a notepad ready to go because you don't want to waste time. Okay? Start trying to write it, and your code will probably look a lot uglier than this. And this is going to be something you can refer back to when you want to make it better. Okay? But I don't think I can make you really grok it in the middle of lecture. Maybe some of you got it, but it's a tough concept. Okay? So this code's it's very compact and clean and a little different than you might imagine. It also has this mysterious line at the end where we return t. That's an important point, but that'll be for later when you guys think about implementation. Okay? The idea, now actually, one thing I want to note is in the middle of the night tonight, when you wake up, just totally drenched in sweat thinking about this, okay? This is what you're going to want to write. If t.left is null, then t.left equals new binary search tree insertion key, and likewise for right. And the surrounding code that goes with this is not going to be as good. Now this approach right here, I'm going to pick on this a few times in class. This is what I call arm's length recursion. It's a more complicated base case than you really need. Instead of looking and saying, are you null? Are you null? Okay, do this. It should be am I null? And what you'll find, it's kind of like sentinel nodes, where it's like hard to think like this, but once you have the right mindset, it's better because this base case is simpler. There's less to think about. So I'd say that this code is nicer, and if you, God forbid, someday write a deletion operation for a binary search tree, which we'll talk about in a little bit, it is far easier if you're thinking in a non-arm's length recursion way as opposed to arm's length recursion. In fact, I'm going to add a little note here, and I have common rookie habit to avoid, but this is, I'll say, arm's length recursion. Okay, no good. Okay, so it feels natural. When you first try and write code like this, you want to do this, but this is better, but this takes more practice. It's like trying to attain some sort of Zen state. All right. Okay, any questions about this? Yes.
Is it always better to do self-recursion?
Is arm's length recursion always worse than, I guess, me recursion? Great question. I don't know. That's a really interesting question. I can't think of any counterexamples, so I don't know though. Yeah. Maybe we'll add that as an A-level question, A++ level question. Yeah. In a piece of code where you're iterating not with a static method, you yourself will never be null. So that's something to think about, but I'll table it for now. Other thoughts? Okay, cool. So now we're going to be able to delete. Why would you ever delete something from a binary search tree? Give me an example. Yeah. Yeah, you have a binary search tree of all your friends. And then maybe, you have a Project 2 partner who's not pulling their weight. And you're like, gotta go. I don't know. You guys should work it out amongst yourselves, but sometimes it just doesn't happen. So you gotta clip them out of the tree. All right. So there's 3 cases. One is that the deletion key has no children. There's nothing special about it, right? There's nothing special about eyes. It's just by coincidence that it has no children. Another is that it has 1 child, and another that we have 2 children. So it turns out the no children case is real easy. You can literally just sever the parent's link. So if I want to delete glut, I just need to set flat.right equal to null. So if I set flat.right equal to null, it goes away. And what will happen to this node in Java? Garbage collection. Goodbye. Okay, so it's gone. So all we got to do is cut the node. That's what deletion means. Okay. How about if we have 1 child? Let's say we want to delete flat. Well, the goal is We want to maintain the binary search tree property so that everything on the left is smaller, everything on the right is bigger. And so what I'll note is that flat's child, it has one child. Why? Because we said this is case 2, key with one child. So flat's child has one child. And what I can tell you is that its child is definitely larger than dog. How do I know that? How do I know that this is going to be larger than dog? Because it's on the right of dog, transitively, right? So we could just move dog's pointer, just point it straight to elf. And in that case, what will happen to flat? It gets garbage collected along with its instance variables. So this arrow, mind you, this is just an instance variable. So it's just going to go like the rest. Okay? So that always works if you have one child, and the argument is that one child is always going to be on the correct side of your parent. So you just have your parent point at your child instead of you, and you're good to go. Now the code you write for that is a little tricky. It has some nice recursion to it, but I'm not going to show it in class. Okay? That'll be a thing to ponder later. Okay, any questions about this process? Yeah. So if you want to delete dog here, how many children does dog have? 2. So that's case 3, and we'll get there. And that's the most interesting deletion of all. So basically the point here is that case 0, I really should have named them case 0, 1, and 2, but I didn't. Oh well. But if you have 0 child or 1 child, plural's going now too, geez. 0 children and 1 child is pretty easy, but then deleting when you have 2 children is hard. So I'll let you guys try. Give it a shot. Make up something. Give you a minute. It's not easy. Okay, I'm going to give you guys the state-of-the-art solution. So, let me give you a general thought about, hopefully you came up with some kind of notion. The goal when you try and delete something that has 2 children is to find, in this case, a new root node. If you have 2 children, you're the root of a tree, you need to find somebody to replace you. So that new root node, it needs to be bigger than everything in your left subtree, and needs to be smaller than everything in your right subtree. So for example, if I take bag, is that going to work? Like let's say I put bag up top, somehow. What am I going to potentially run into? So I just somehow move bag up. What do I have problems with elf and cat? Yeah, cat should not be to the left of bag. So yes, you have to manipulate some arrows, and it's like, what do I do? I think the bigger concern is that if I choose bag to be the new boss, which I'm sure for many of you was tempting. It's like, okay, well, I'll somehow grab E and bring it up. I'm going to run into trouble. Okay? I don't know. Somebody want to maybe give me a thought about how they might do it? So if I try and move E up, the point here is just when I do this, I'm going to have some kind of horrible problem that involves G and F. I need to get them over here or something. So anybody have any other thoughts? Yeah. 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 So if we do something like that, we don't want E to have 3 branches. So we need to do something. Yeah.
We could bring either the smallest value in the right subtree or the largest value in the left subtree.
Yeah. So the suggestion there was, rather than, there is a workaround. You can make E the new boss. Okay? Get out of here, okay? You can make E the new boss, but it is going to be just a living nightmare, okay? The better approach, which you just hinted at, is to pick a different successor, okay? So another approach is to pick a better successor. For example, you could choose either cat or elf in this tree. And that would be a great new boss, because we put cat up top. Then it means that these can be on the left. If you pick cat, then bag and elf are on the left just fine, and all these are on the right just fine. Okay. Now what's nice about this is that if you pick one of these as your successor, sorry, not only do I have something in my throat, but something in my eye, which is a new challenge I'm facing in the middle of teaching. But we're here together. We'll do it. Wow. All right. I took a bite of a cookie. I think Eli poisoned me so that he can be in charge of the class. So if Eli shows up on Friday, it's like, I don't know where Josh is. Go looking for me. I don't know where Eli lives, but maybe one of you guys does. All right. So what I could do is pick either cat or elf. And what's nice about that is they are guaranteed to be either case 1 or 2. So cat, you'll notice, has no children, and elf has only one child. I'm telling you that it doesn't matter. No matter what, the item over here, so the smallest item in the right subtree, that's the successor here, it's only going to have one child. How do you know that to be the case? So maybe we frame this question real quick. I want to either pick the largest item in the left subtree or the smallest item in the right subtree to be the new boss. How do I know that Eli is killing me? How do I know that, go ahead. Yeah, so the largest item on the left subtree, it cannot have a right pointer. It would be impossible. Then it wouldn't be the largest item. So by definition, if you are the smallest something in a tree, you have no left child, because otherwise you're not the smallest. Okay, so you're either case 1 or 2. So now try deleting K again. If that made sense, it will be easy. If I was too busy coughing and cursing Eli, maybe it won't. Give it a shot. Yeah. So the solution's not showing yet, but G and M, those are your buddies you want to think about. All right, let's try it out. Okay, so we want to delete K. It's gone. We're either going to take G or M and make them the new boss. So what do I need to do with G? Delete it. So it's gone. If you delete it, that means taking its parent and pointing it at F. And then we'll take the original pointer that we kept a reference to, and we set it there, G. So that's the new tree. So we made G the new boss. All right? So those are the same. Any thoughts? Yeah. Let's say you don't move. Okay, let me try that real quick. You don't move G up. You move what? That entire tree under G. Let's see. That construction maybe works. Let me think about it. So you take the old right of the boss and hang it below. I'm not sure. I'd have to think about it. In 30 seconds, I can't think. What's that? So these all need to be bigger. It's not guaranteed. It's not guaranteed to work. Yeah. I think, right? It's a point of contention, but guess what? We only have 30 seconds. So, does this alternate deletion procedure work? It's a problem to think about. Okay. So let me say one thing that's very important about BSTs before we go. The height between a bushy tree and a spindly tree varies dramatically. This is a bushy tree, very fast. This is a spindly tree, very slow. Now, because I went a little overboard on giving you guys time on insertion, I'm not going to give you a chance to actually answer this question. So we already know that the runtime for operations on a tree like here will be log n. What will they be here? N. No good. So in fact, we will see that if we insert into a tree randomly, now there's some good news, which is that if we insert into a tree randomly, it preserves pretty good height. On average, it'll be log n height. But if we delete, there's a funny thing that if you do random insertions and deletions, using the deletion we did in class, over time the tree will change from log n to square root n. And this is actually a really surprising result way back in the day, I think in the 60s, maybe 70s, where they ran simulations and were like, that's weird. If we insert and delete the way we just described, we end up with square root n. And to this day, no one's found a better delete procedure that avoids this issue, where deletion doesn't cause the tree to eventually get longer. Okay, so it's like an emergent property of many inserts and deletes, and the proof's pretty sophisticated. So in the next lecture, what we're going to do is get around this problem by coming up with a better insertion procedure that will avoid the whole problem. All right, thank you. And if you see Eli, ask him for the antidote. Thank you. All right.